Hello everyone, welcome back to Tiny Tech Talks. We are currently racing towards two massive technological horizons, autonomous AI agents and quantum computers. But here's the problem. They are on a collision course. Most AI agents today communicate over standard TLS 1.2 or TLS 1.3. They use RSA or elliptic curve signature to handshake with the API. To a quantum computer using Shor's algorithm, those secure connections are basically open doors. If an attacker captures your agent's traffic today, they can't read it now, but they can store it and decrypt it the second a cryptographically relevant quantum computer goes live. We call this harvest now and decrypt later. If your agent is handling company secrets or financial data in 2026, you are already at risk. To solve this, we don't need to panic. We need to migrate. NIST has officially released the first set of post-quantum standards. As architects, you need to know these three. First, FIPS 203, which is ML-KEM, formerly known as Kyber. This is for the agent key encapsulation. It's what secures the tunnel your AI agent uses to talk to a vector database. Second, FIPS 204, which is ML-DSA, formerly Dilithium. This is for digital signatures. When your agent says, I'm agent 7 and I have permissions to move these funds, ML-DSA is what proves it's really the agent and not a quantum-powered imposter. Third, FIPS 205, SLH-DSA, a stateless hash-based signature. It's slower but acts as a plan B because its security isn't based on the same math as the others. Let's get technical. If you're building AI agents in Java, you don't have to write these algorithms from scratch. Libraries like Bouncy Castle already have support for ML-KEM and ML-DSA. ML-KEM is used to establish a shared symmetric key, like AES, between two parties, example, an AI agent and a database, in a way that quantum computers cannot break. Now let's look at this example. I'm calling this class as PQC Agent Security. The first step is to set up the post-quantum provider, which is Bouncy Castle in my case. The next step is to generate ML-KEM key pair. Here, you will have to go for get instance and generate the key pair. The third step is to encapsulate on the sender side, which is the AI agent in our case. Just go for KEM get instance, create a new encapsulator and encapsulate it. After the encapsulation is done, generate a secret key which is for the sender and create an encapsulated message in this way. The next step is to decapsulate, which is on the receiver side, which may be a secure vault in our case. Now, again, we will create the same KEM get instance and we will run the decapsulator. The next step is to decapsulate. Here we are going to pass on the same encapsulated message to decapsulate. Now, both parties share the same 256 AES key and which is also decapsulated and encapsulated using the Bouncy Castle ML-KEM algorithm. In Java, this looks like updating your security.add provider to include the latest PQC providers. The challenge isn't the math, it's the key size. PQC keys are significantly larger than RSA keys. You need to account for this in your network overhead and database schemas now, or your agentic workflow will hit a performance wall later. When you're building your agent sandbox or your identity manager, you should be implementing a hybrid handshake. You should keep your classical X25519 for backward compatibility, but you should wrap it in an ML-KEM layer. Now let's look at ML-DSA, which was called Dilithium earlier for digital signatures. ML-DSA ensures that the command sent by an AI agent hasn't been tampered with and truly originated from the trusted source. Let's look at the example here. Here again, we are going to add the provider, which is Bouncy Castle provider, and we are going to generate ML-DSA key pair. Again, we are going to go for get instance, and then we will generate the key pair. The next step is to sign a command. For example, in our case, the agent command is action transfer funds amount 100 from account A to account B. Here we'll have to generate a signature. Again, we'll go for get instance, and notice here we are passing on ML-DSA. Then we'll initialize the signature and update it, and in the end we will create a signature. For the simplicity purpose, I've again put the signature for the sandbox side in the same code. Now again, for the verifier, you go for get instance, you initialize the verification and update it. In the end, you'll have to check if the signature which has come from the agent side is the same or not, or is it valid or not. If it is valid, then you allow. If it is not valid, then you don't allow the transaction to happen. As a developer, notice that these keys and signatures are much larger than RSA or ECC. For example, ML-DSA's 65 signature is roughly 3300 bytes compared to just 64 bytes for ED25519. Your database columns for storing these must be updated to either a blob or var binary 4000. Let's talk about performance now. Java 21's KEM API is highly optimized. Please note that while the keys are larger, the mathematical operations, which is the lattice-based operation, are often faster than the modular exponentiation used in RSA. In production, you wouldn't just use ML-KEM. You would combine it with a classical key like ECDH in a hybrid mode. If one is broken, the other one still holds the fort. Time for today's tech tip. Don't wait for a quantum computer to exist to start migration. Start with crypto agility. Instead of hard coding specific algorithms into your agent's security layer, use an abstraction or a provider pattern. This allows you to swap out RSA for ML-KEM via a simple configuration change without refactoring your entire codebase. If your agent security is modular, it is future-proof. Quantum safe AI isn't just a niche topic. It's the next standard for enterprise architecture. If you found this deep dive helpful, hit the like button and subscribe for more bite-sized tech talks. I am Amit and I'll see you in the next one.